All right, so let's look at some odd, even questions. So what about this function? Let's look at f of x equal to, what do I got here? X to the fifth times the square root of x to the fourth plus 9. So if I want to see if whether I'm, so my kind of process for seeing something's even or odd or neither is always, always, always to start with f of negative x. And let's see what you've got. So that's going to be negative x, right? You're just replacing every x with a negative x in parentheses. And then doing whatever else after that. That's going to be negative x parentheses to the fifth times the square root of negative x parentheses to the fourth plus 9. Even powers get rid of the negative. Odd powers retain the negative. So negative x to the fourth is a negative times a negative times a negative times a negative, which is positive. Negative x to the fifth is one more negative, so it's going to be negative. This is going to be negative x to the fifth times the square root of x to the fourth plus 9. So now the question, does this equal the original function? No. The original function is that, this function is that. They clearly differ by a minus sign. But that gives me a good idea that it's probably an odd function. So no, it's not equal to the original, which means it's not even. Is it equal to negative f of x? It is, right? Because I can just rewrite this as negative x to the fifth times the square root of x to the fourth plus 9. And that is equal to negative f of x. Yes. So it's odd. Cool. Let's look at another example. I think I might change this next example up. Do I really want to change it up? Yeah, I think I do. Yeah. Let's look at, say, I'm always kind of like, sure. Let us look at f of x equal to, yeah, I've got it. How do I want to do this? The square root of 7 minus x squared divided by x cubed minus x. All right, so again, same process. We're going to start with f of negative x. It's going to be the square root of 7 minus negative x squared over negative x cubed minus x. Minus x. Careful there. So let's see. Simplifying. So I want people to be careful because I've definitely seen people kind of simplify this kind of thing wrong. When you got a minus parentheses minus x squared, just deal with the parentheses first. Negative x squared is just x squared. So then I've got just 7 minus x squared. Divided by negative x cubed is negative x cubed. Negative x is positive x. Is this equal to the original? I don't think so. Right? The tops are the same, but the bottoms are different. So they're probably not the same. What about, is this odd? So let me ask you guys. So here, instead of trying to factor out a negative from it, I would probably write negative f of x. So negative f of x is negative of this. Okay, so here's something to be careful about. When you multiply a negative by a fraction, like I could say a negative 1 times the fraction. Actually, in fact, let me ask you guys, if I did like, negative 1 times 5/3, you could either write it as negative 5/3 or 5 over negative 3. But it's not negative 5 over negative 3. What I'm trying to say in the longest way possible is that when you multiply a fraction by a negative, you don't multiply the top and the bottom by the negative. Because if you multiply by a negative 1 or a negative 1, you're really multiplying by just positive 1, which is not what we're trying to do here. So we can multiply the top or the bottom, but not both by negative 1. I want to think of this as actually multiplying the bottom because that's the part that looks different. So I'm going to think of this as -1. I'm going to rewrite as 1 over -1. Those are equal, right? 1 divided by -1 is -1 times the square root of 7 minus x squared over x cubed minus x. And now I'm going to distribute the -1 to x cubed minus x. So that's going to be square root of 7 minus x squared over -x cubed plus x, which is equal to that. So it is odd. So f of -x equals -f of x, odd. I also want to mention, if you did multiply the top by -1, there's no distributing to do. You can't distribute the -1 through a square root. You can only distribute multiplication across addition or subtraction. So if you've got other weird functions in the way, we cannot distribute multiplication like that. Okay, so that's all I want to say about the odd even, or all the extra stuff I want to say about odd even. I think my wife just turned on the heater. I think I'm going to have to turn it down because it's really hot in here. 1 second, let me go turn down the heater. Yeah, it's too warm in this room. Also, she has like a space heater in her office that is very warm. She should be using that. Let me be cool. All right, so let's move on to class O. So class O is graphing rational functions. So a rational function is a function that looks like a fractional kind of thing, and it's a polynomial divided by a polynomial. So rational function is something like f of x equal to polynomial divided by another polynomial. And they typically should be different polynomials. Technically, they could be the same. That would be weird because you'd essentially just be graphing one. Yeah. Here's a couple of examples. We're not going to graph this. I'm just giving you some examples. So f of x equal to x squared over x to the 4th minus 1. The top is definitely a polynomial. The bottom is definitely a polynomial. Or g of x equal to x squared minus 3x plus 1 over 3x squared minus 1. Also a polynomial divided by a polynomial. Or even something like let's use dash or g of x again. Why not? G of x equal to x cubed plus 1 over 2x squared. Or even something like h of x equal to 4 over 6x squared minus 1. Yes, even this last one is a polynomial over a polynomial. A constant is a polynomial. It's just a really boring one. Okay, so a few things to consider. When we graph polynomials, we're going to use a template that is very similar to the one we did for, when we graph rational functions, we're going to use a template that is very similar to the one we use for graphing polynomials. We're going to find the y-intercepts, we're going to find the x-intercepts. We don't so much have an end behavior kind of thing, but we are going to talk about the multiplicity of the x-intercepts. And then we're also going to additionally find two other features, vertical asymptotes and horizontal asymptotes. So a vertical asymptote, which we will often abbreviate as a VA, so vertical asymptote, VA for short, is a vertical line, right? Hence the name. It's a vertical line. So it's going to be like x equal to something, x equal to a constant. And we find them so I want to be a little bit extra clear about this. To find them, we're going to set the denominator equal to 0. But before we do that, the thing we're going to do, if we can, is factor and cancel any factors that cancel. So basically, you should be setting the denominator of the simplified form equal to 0. So we're going to find them. We set the denominator equal to 0 and solve for x. So for example, this function, f of x equal to x squared plus 1 over x squared minus x minus 6. Well, I would factor it. The top doesn't factor. The denominator factors is x minus 3 times x plus 2. Nothing cancels. So we're going to set the denominator x minus 3 times x plus 2 equal to 0. And then we're going to get x equal to 3. And we're going to get x equal to negative 2. So this rational function has a vertical asymptote at x equals 3 and at x equals negative 2. To contrast this, because I do want to show you guys this, if instead my function was x squared minus 4 over x squared minus x minus 6, before I find the vertical asymptotes, the numerator factors is x minus 2 times x plus 2. The denominator factors as x minus 3 times x plus 2. And the x plus 2's cancel. So this equals x minus 2 over x minus 3. And their vertical asymptote is only when x minus 3 equals 0 or when x equals 3. This one does not have a vertical asymptote at x equals 2. Sorry, x equals negative 2, because that factor cancels out. That's not something that's going to come up a whole lot, but it does come up occasionally, so I felt like I should mention it. Functions don't cross their vertical asymptotes typically. It is possible to make up a weird piecewise function where we're not going to graph this one really, but I can totally, if I really wanted to, I can make a piecewise function that had, say, something like a vertical asymptote at x equals 2, and on the right-hand side did something like this, and the left-hand side was defined to be something like that. Right? This could be the graph y equal to the square root of negative x minus 2. Right? I went to, no, I think they were plus 2. Yeah, plus 2. When x is less than or equal to 2, and 1 over x minus 2 when x is greater than 2. So there's an example of a dumb function that crosses, or at least touches, its vertical asymptote. You shouldn't worry about this. I would never like ask you about this, but just be aware. When people say you can't cross a vertical asymptote, they're generally right, but someone could try to make up a dumb example where it still did cross. Yeah, so vertical asymptote, the function doesn't cross it, right? Because you'd be dividing by 0 there. And more importantly, the graph, when you have a vertical asymptote, gets infinitely large or negatively infinitely large. So if I was actually graphing, instead of this silly graph, if I was just graphing, say, y equal to 1 over x minus 2, this graph definitely has a vertical asymptote at x equal to 2, right? X equal to 2 makes the denominator 0. There are no there's no x-intercept, because this fraction never equals 0. There is a y-intercept when x is 0, y is 1 over negative 2, which is negative 1/2. And so what happens is, when x is bigger than 2, this whole thing is positive. Like when x is 3, y is 1. And then as x gets very, very large, y gets very, very small. And as x gets closer and closer to 2, the y values get very, very large. Because a number close to 2 minus 2 is very, very small. And then 1 divided by a very, very small number is very, very large. And then on the other side, the same kind of thing is happening with the negative. You could also, I suppose I could also frame this as it's the 1 over x graph shifted to the right. But I want to stress, when you have a vertical asymptote, on either side of it, the function is either going up towards positive infinity or down towards negative infinity. And you can have 4 different things happen. You can have both sides up, both sides down, one side up, one side down, or the other side up, the other side down. So there's 4 different options around a vertical asymptote like this.
Can I ask a clarifying question about that?
Of course.
Are there any distinct features within a rational expression that permit us to understand the direction of the graph? So for this one, we had 1 over x minus 2, and we determined the end behaviors of each thing we graphed.
So I didn't determine the end behavior really. So there is end behavior for these graphs, but it's kind of it's encompassed by talking about the horizontal asymptotes, which we're going to do next.
Okay.
I will say there is a way using multiplicity of the asymptote to tell whether both sides go the same direction or opposite directions. And it's actually the same kind of thing that's true about the multiplicity of an x-intercept. So if an asymptote has, so this asymptote x equal to 2 came from this factor, which has an odd power. And when the asymptote has an odd power, it goes opposite directions. One side goes up to infinity, the other side goes down to negative infinity. On the other hand, let's just look at a very similar example. If your function is, say, 1 over x minus 2 squared, well then, this pen is starting to die. You were a good pen. I'll miss you. This one looks good though. So, yeah, that's a great pen. So here, x equals 2 is also a vertical asymptote. But you can see that since I've got 1 over something squared, every value is going to be positive. Right? Yeah. So when x is 3, y is 1 over 1. When x is 1, y is 1 over negative 1 squared is still 1. And then as x is closer and closer to 2, the y values get very, very large. As x is closer and closer to 2 from this side, the y values are very, well, the insides of here are very, very small and negative, but a negative small number squared is a positive small number. And 1 over a small number is a big number, a positive big number. And then it does this kind of deal. So here, the vertical asymptote x equals 2 came from the factor x minus 2, but it was to an even power. And so the even multiplicity means that both the asymptotes go in the same direction. The odd multiplicity means that, both sides of the asymptote go in the opposite direction. So odd, opposite, even, the same. It almost works. Okay.
I understand. Thank you.
Welcome. There are other ways to determine which way things go by like just picking some extra points. But yeah, we will talk more about that as we go on. I also want to emphasize, and this is really a really important piece of information. The graph can't cross the x-axis if it doesn't have an x-intercept. Right? So both of these graphs don't touch the x-axis anywhere because neither of these functions can ever equal 0. A fraction can only equal 0 if the numerator is able to equal 0. 1 is not 0. 1 is not 0. So these both fractions both can never be 0, which means they can both never have an x-intercept. Okay. Horizontal asymptotes. There's a little bit more to say, but we'll try and sum it up. Which we abbreviate as HA. So for rational functions, like the ones we're talking about, if there's a horizontal asymptote, it is the same on the left and the right side of the graph. There are other strange functions that can have a different horizontal asymptote to the right and a different horizontal asymptote to the left. We are not dealing with that in this class today. Maybe, but just be aware that you can have, a function can have actually 2 different horizontal asymptotes, which is kind of weird. So here's how we do it. In fact, let me just, I feel like it's almost easier with an example. So I'm just going to tell you this function, f of x equal to, sure, let's do 2x over x squared plus 1. That function has a horizontal asymptote of y equals 0 because the degree on top is less than the degree on the bottom. If the degree on top is less, right? So if you think about this, and I should back up a little. When you're talking about a horizontal asymptote, you're asking what's happening to the function at the ends, meaning as x is getting really, really big or really, really negatively big. Okay, well, if I've got a big number divided by a big number, well, here's the thing. The denominator here is going to be a bigger number because it's x squared. The numerator is just 2x. So if you pick like something like, x equal to 1,000, on top you're getting 2,000. On the bottom you're getting 1,000 squared, which is 1,000,000 plus 1. 2,000 divided by 1,000,000 is going to be pretty small, right? I mean, disregard the 1 there for a second. It's essentially just 2,000 over 1,000, which is 2 over 1,000, which is 1/500th. So when you have a degree that's less on top than it is on the bottom, the fraction is going to get very, very small as x gets very, very large, which means the function values are going to get closer and closer and closer to 0. So here is the first step. Or I should say, before we do anything, we're going to look at the degree or degrees of the top and bottom. So there are 3 things. If the degree on top is less than the degree on the bottom, then your horizontal asymptote is y equal to 0. Boom, done. Okay, and then on the other hand, if the degree on top is bigger than the degree on the bottom, which is not our favorite case, you're going to have no horizontal asymptote. So here's the deal, right? To have a horizontal asymptote, the function has to be getting close to a real number. But if the degree on top is larger, like for example, if we had something like f of x equal to x squared over x plus 1, well, now we've got the reverse sort of situation where the numerator is getting big fast and the denominator isn't. So if you plug in 1,000, you're going to get like 1,000,000 over 1,000, which is like 1,000. Or if you plug in 1,000,000, you're going to get like 1,000,000 squared over 1,000,000, which is going to be like 1,000,000. So this one, the function is going to get very, very large to the right and very, very negatively large to the left. But we're not getting close to any one particular number, right? The function is just getting bigger and bigger and bigger forever and ever and ever. So that means there's no horizontal asymptote. The horizontal asymptote is a horizontal line that the function gets really, really close to. I guess I should have written that. Right? It's a horizontal line of the form y equal to some constant c. And the third case is the most interesting case, which I guess I wrote them out of order from what I did in the notes. Oh well. So if the degree on the top and the degree on the bottom are equal to each other, then the horizontal asymptote is y equal to a fraction. And the fraction is the leading coefficient of the top divided by the leading coefficient of the bottom. So for example, I'll give you 2 examples. If my function is 3x squared plus 2x plus 1 over 4x squared plus 9, the degrees are the same. What's the horizontal asymptote going to be? It's going to be y equal to the quotient of the leading coefficients. The leading coefficient on the top is 3. The leading coefficient on the bottom is 4. So the horizontal asymptote would be 3/4. In a similar way, and this is the one I'm going to try and trick you with this one. If g of x was equal to 5x minus 2x cubed over 6x cubed plus 3x plus 1, what is the horizontal asymptote here? It's not 0. It's a good. So I can see why you might answer that question that way, Alessandra. So I'm guessing that you're guessing 0 because you're saying that the degree on top is less than the degree on the bottom. It's okay. It's all right to make mistakes. I make mistakes all the time, as you guys, I'm sure, are very aware. So yeah, it is negative 1/3, exactly. And the way that we are getting that, for those of you that don't see the answer, is the degree on top is 3. The degree on the bottom is also 3, right? The highest power is the degree that's in the top or the bottom. So then the leading coefficient on top isn't 5. I was thinking someone might say the answer was 5/6. The leading coefficient on the top is -2. The leading coefficient on the bottom is +6. So the horizontal asymptote is y equal to -2/6, which is -1/3. So, yeah. So that's how you find horizontal asymptotes. If the degrees are the same, you look for the quotient of the leading coefficients. But you do have to recognize that the leading coefficients are the coefficients of the terms of the highest powers. They're not necessarily going to be the things written first. They should be if we're writing it in the standard form. Sometimes people like to write things in different ways. So let's look at some examples. And we'll also mention that just like with the polynomial graphing, there are also templates for the rational function graphing. So let me share just for a moment. Not that, and you guys don't have to use these at all. Honestly, it's more for like when we're in person. But if you look here, there's the graphing rational template. So if you look at that, of course, it'll probably take forever. No, actually, come on. So right, here's all the things, and we won't talk about slight asymptotes today, but we will talk about them on Monday, also called obliques. So you look for the horizontal asymptote, you look for the y-intercept, you look for the x-intercept, you look for the vertical asymptotes. I'm going to skip the number line, and then we'll do the graph. And yeah, and we'll say a few extra things here, but that's kind of the deal. That's what we're going to do when we're trying to graph stuff. Okay, example time. So I want to graph f of x equal to x plus 6 over x minus 2. And I typically, although the template kind of starts with the horizontal or slant asymptote, I usually start with, I can see why they start with that though. They're probably starting with that because it's kind of like starting with the end behavior. So for lack of a better word, if there is a horizontal or slant asymptote, sometimes there's neither. We will talk about slant later. That's kind of like your end behavior. So I guess it would maybe make sense to talk about the fact that the horizontal asymptote here is, well, the degree on top and bottom are both 1. So the horizontal asymptote is going to be y equal to the quotient of the leading coefficients. The leading coefficients are both 1, so it's going to be 1 over 1, which is y equal to 1. So here's what that means for our graph. And sometimes I like to start just putting stuff on the graph from the get-go. So here's y equal to 1. And what it means is it doesn't really have any effect on what's going on in the middle. But it means is way out to the end, we're going to either be getting close to it like this or close to it like this. Right? Our graph has to get closer and closer to the horizontal asymptote, which if you think about what we have here makes sense, right? If you've got x plus 6 divided by x minus 2, if x is really, really, really large, like if x is a million and 6 divided by a million minus 2 is 999,998. That number is really close to 1, right? It's not equal to 1, but it is equal to 1.000008, right? It's super close to 1. Whereas in the middle, right, if you plug in, like say 1, you get 7 over -1, which is -7. So the horizontal asymptote is telling you about the end behavior of the function. Way out to the right, way out to the left. Doesn't have a thing to say about what's going on in the middle, really. Okay, that said, I still usually start by finding the intercepts. So the y-intercept, we're going to set x equal to 0. We're going to get y equal to 6 over -2. So 6 over -2 is -3. So 0, -3. And then for the x-intercepts, here's a nice thing about rational functions. So for x-intercepts, you can do the long method of setting the whole thing equal to 0. But if you're setting the whole thing equal to 0, your first step is going to be to multiply both sides by the denominator. So I multiply both sides by x minus 2. On the left, x minus 2 times x plus 6 over x minus 2, they cancel. I guess I could write it out. I guess I could show my steps. So we multiply x minus 2 times this, I get x plus 6. X minus 2 times 0 is just 0. So what I want you all to see here is that instead of setting the whole thing equal to 0, you can just set the numerator equal to 0, and that's equivalent. Because we said before, right, the only way for a fraction to equal 0 is for the numerator to equal 0. So if x plus 6 equals 0, x equals negative 6. So that's an x-intercept. In the way. Okay, and then I need to find my vertical asymptote, which is going to be, so set the denominator equal to 0, which in this case is going to be x equal to 2. That's going to be a vertical line through 2. You don't have to label them if you've written it somewhere else and it's clear what it is, but I'm labeling it so you guys can see, oh yeah, the vertical line is x equals something, the horizontal line is y equals something. And now we're going to try and graph it. And so here's kind of my technique for graphing. You can plot more points if you want. I don't want to unless I have to. So here's what I'm going to do. I'm going to say, okay, from this y-intercept here, we're stuck. Meaning we can either go, so I should say more. When we come close to this vertical asymptote, we have to do one of two things. We either have to go down to negative infinity or up to positive infinity. But we're forced to go which way? Do we have to go down or do we have to go up?
We have to go down.
Right. And now there's a reason we have to go down. And I'm imagining somebody's probably going to guess the wrong reason, and that's okay. Let me ask you guys, why can we not go up? What's preventing us from going up?
The horizontal asymptote.
That is the wrong reason I was looking for.
Oh, that's great. Okay.
It's okay though, right? So here's what I want everybody to know. A graph can cross its horizontal asymptote. It doesn't have to cross it. It doesn't usually cross it, but it can cross it. There's another, though, reason that is preventing us from going up. And it's the fact that we can't cross the x-axis if we don't have an x-intercept. There's no x-intercept there, right? We're stuck. We have to go that way. So that's the thing I really want you all to keep in mind, is that if you don't have an x-intercept, you cannot cross the x-axis. So when you're approaching a vertical asymptote, you have to either go down to negative infinity or up to infinity, and one of those directions will make you cross the x-axis when you're not allowed to. So you have to go the other way. All right, on the other side of this vertical asymptote, this is where you have a choice. So I will also mention, right, if you don't like this, you could also plug in like 1. If you plug in 1, you get 7 over negative 1, which is negative 7. So you could also say, oh yeah, down here I have the point 1, negative 7, which is kind of showing me that we're kind of going up. Over here, you have a choice. You can either do what we just did, say, I'm going to plug in 3. If you plug in 3, 3 plus 6 is 9, 3 minus 2 is 1, 9 over 1 is 9. So you get some large value up here. But you can also do the thing I was saying before about the odd or evenness of the vertical asymptote. The vertical asymptote came from this factor, x minus 2 to the first power. Since it's an odd multiplicity for our vertical asymptote, we have opposite behavior. One side goes down, the other side has to go up. Now, I'm going to draw this not perfectly. Shock of shocks, I know. Because I want to be able to show the horizontal code. What's happening is it's going to come down this way, and then as we move to the right, the function has to get to the right. There's nothing else to deal with. The function is going to get closer and closer to its horizontal asymptote. All right, we still have to deal with the left-hand side. So to the left, there's only two things to deal with. There's this x-intercept, and there's this horizontal asymptote. So at this x-intercept, are we going to cross or are we going to bounce? Well, the x-intercept of negative 6 came from the x plus 6 to the first. The x-intercept has an odd multiplicity. So I suppose I could have written that down over here, right? The multiplicity here is 1, which means we're going to cross. Also, if you didn't want to think about that, you could well be like, well, there's a problem, right? I'm going to draw it wrong. If we bounce off, how are we ever going to get close to that horizontal asymptote? We can't, right? There's no more x-intercepts to go through. That's not allowed. So that's another reason why you're kind of forced to do what you already know you had to do. So yeah. So a lot of this graphing of these rational functions, in my opinion, is kind of being like, well, we've eliminated all the other things that are possible, so it's got to be this, right? You're kind of forced to draw your graph the right way if you pay attention to the things that you have and the things that you don't have. Okay. Let's look at more examples. Let's see. So let's graph f of x equal to 2x squared over x squared minus 1. And I'm gonna do the way I usually do it, even though the horizontal asymptote we can see. So first thing, we're gonna find the y-intercept. So setting x equal to 0, y is gonna be f of 0, which is 0, or 2 times 0 squared, over 0 squared minus 1, which is 0 over not 0. Right? 0 over 0 is a problem, which we shouldn't encounter. 0 over 0 is undefined. 0 divided by negative 1 is just 0. X-intercepts. Well, we know 0 is going to be one of them, right? If the y-intercept is 0, an x-intercept is also 0, right? There could be other ones, but at least that. So I'm going to do the shortcut method and just set the top equal to 0. So I'm going to set 2x squared equal to 0. And oh yeah, our solution is going to be x equal to 0. Okay. X squared equals 0 divided by 2, x equals 0. With a multiplicity of 2. Meaning at this intercept, it's going to bounce. Okay. Vertical asymptotes. We're going to set the denominator equal to 0. So we're going to set x squared minus 1 equal to 0. Now here's my board of advice. You totally could add 1 and then take the square root of both sides and get x equal to plus or minus 1. But factoring is going to be a better way to see the multiplicities of the asymptotes if you want to do that kind of thing. So I'm going to factor this as x minus 1 times x plus 1 equal to 0. And we're going to get x equal to 1 and x equal to negative 1. And since they both came with factors with odd powers, that means they both have odd multiplicities, which means both of my asymptotes are going to be opposites, right? One side going up to infinity, one side going down to negative infinity. We'll also check the point, but I want to point out that this is how I like to do. Ooh, that was loud. I like to do it that way. It's because I've got my volume turned like all the way up. So, and then lastly, the horizontal asymptote. The degrees are the same, right? Degree 2, degree 2. So the horizontal asymptote is y equal to what? 2 over 1. Right, leading coefficient here, leading coefficient here. I do want to mention it's not because the degrees are both 2, right? Even though I know the degrees are both 2 and the horizontal asymptote is 2 here, and on the previous one, the degrees are both 1 and the horizontal asymptote is 1, because we're comparing, really, we're dividing those leading coefficients. All right, we've got all the information. Let's put it on a graph. So let's see. Y-intercept of 0. X-intercept of 0. Okay, good. Horizontal asymptote of y equal to 2. Vertical asymptotes at positive 1 and negative 1. Now, there is a small problem in that, and this is always true if you're starting at the origin. We're not on either side of the x-axis yet, right? We're not above or below. So we don't have a way of knowing if we should go up or go down. And I do want to stress here, it is possible that we could go up, right? Because you can cross a horizontal asymptote. We don't, but it's possible. So in this sort of case where you don't know which way you go because you're starting with the origin, it is usually a good idea to test another point. So I'm going to test x equal to 1/2, right, between 0 and 1. If I plug in 1/2, I get 2 times 1/2 squared over 1/2 squared minus 1. 1/2 squared is 1/4. So 2 times 1/4 over 1/4 minus 1. I don't really care what the value is. I just care whether it's positive or negative. This is going to be 2/4 on top over negative 3/4 on the bottom. So it is going to be a negative number. It's going to be negative 2/3 because the 4's cancel out. So when you go to the right here, you do go down like that. And then now that we're on the side of the x-axis that's below, we have to stay below. The asymptote is an odd multiplicity asymptote. So on the other side, if this side's going down, this side's going up. You could also test a point, right? You can test x equal to 2. And if you plug in 2, you get 2 times 2 squared, which is 2 times 4, which is 8, over 4 minus 1, which is 3. So you get 8/3, which is positive. So when you plug in 2, oh yeah, we're getting 8/3. That is totally fine if you want to do it that way. And now we'll do the other side. I will mention this function's even, right? If you plug in negative x, you get f of negative x equal to f of x. I don't usually notice that, but if you notice that, right, negative x squared minus 1, that's just 2x squared over x squared minus 1. That means we have even symmetry, which means the other half of this is going to be a mirror image of this. So we should also be going down this way. And we shouldn't be crossing our vertical asymptote like I've drawn it there. Sometimes it's hard to, sometimes your graph, you mess it up because you're not doing a good job. And then this is opposite, so it should be up like this. So this graph totally has even symmetry. Just nice. It does make, if you notice a graph is even or odd, it does make it easier to graph it, because once you've graphed one side, if it's even, the other side is just the reflection, and if it's odd, the other side is the reflection and a reflection. That's kind of cool. How many more examples do I have? Just like one. That's good because we only have time for one, really. That's unfortunate. I want to do a different example. Okay, so I'm going to try and squeeze in an extra example here. I might need an extra couple minutes. Sure, let's do this one. This one's not too terrible. This one will be pretty easy. Let's do f of x equal to x minus 3 divided by x squared plus 4x plus 4. Okay. So let's find all the things. Y-intercept. Set x equal to 0. Y is going to be f of 0, which is 0 minus 3 over 0 plus 4. Okay, don't write all the zeros. So you get negative 3/4. X-intercept. Set the top equal to 0. X is going to be 3. With a multiplicity of 1, because it is x minus 3 to the first. Vertical asymptote set the denominator equal to 0. So x squared plus 4x plus 4 equals 0 factors as x plus 2 times x plus 2. So what's our vertical asymptote? X equal to, all right, well, short on time, you know how it goes. Vertical asymptote is negative 2, and the multiplicity is 2. Because really I should be writing this as x plus 2 squared. So it is a multiplicity of 2, which means they're either both going to go up or both going to go down at the vertical asymptote. Lastly, the horizontal asymptote. Well, since the degree on top is 1 and the degree on the bottom is 2, the degree on top is less, the horizontal asymptote is y equal to 0. Let's graph the thing. So let's see. Okay. So let's see. I've got a y-intercept of negative 3/4, so that's just a little bit above negative 1. X-intercept of positive 3. Vertical asymptote at negative 2. And when the horizontal asymptote is y equals 0, you don't draw it, right? It's just y equals 0, which is the x-axis. Okay, so let's see what's going to happen here. Let's see, I have enough room. Yeah, I have enough room. Okay. So from here, let's go to the left first. So to the left, we have to go downward because again, we can't go up and cross the x-axis there. Not because it's the horizontal asymptote, because it's the x-axis and we don't have an x-intercept. Now this vertical asymptote is an even multiplicity one, meaning the other side should be going the same direction. If you don't like that, you can also test the point. And you can test negative 1, 2, 3. Plug in negative 3. The top is negative 6. The denominator, well, if we think about the denominator, and this is why it's good to actually factor it, so it's easier to plug things in. If the denominator is x plus 2 squared, negative 3 plus 2 is negative 1, negative 1 squared is positive 1. So negative 6 over 1 is negative 6. So yeah, over here it's also negative. Great. And then, sorry, I'm running out of room here. We're going to get closer and closer to the horizontal asymptote of y equals 0. On the other side, we have to hit that number there, x-intercept, and we're going to cross, right? And then my graph, I'm gonna make it look a little bit nicer here. I'm gonna make my x scale look not quite so large. Yeah, sorry. Just trying to make it look a little better here. Oh, come on, graph. Look good. Sometimes it's good to check things out on distance. Okay, so here's the deal. This graph crosses the x-axis at positive 3. And right, so when x is less than 3, like 2, you definitely get negative values. Like if x is 2, you get negative 1 over 4. But when x is bigger than 3, you get positive values. Like when you plug in 4, you get positive 1 over 36. So the thing is, we're crossing there, but then, and let me exaggerate this. Right, so we cross, the graph keeps going up, but then like it has to turn around to get closer to the horizontal asymptote. So we have to do something like that. It's not going to look exactly right. That's fine. So in this case, so the graph will be like, yes, exactly. It was exactly the point I was just going to make on it. Is here is an example of a graph crossing its horizontal asymptote. Sometimes graphs have to cross their horizontal asymptotes.